Hi, welcome to our fourth lecture, the one-pot Halex Sonogashira reaction. This lecture is dedicated to my friend Mubashar, who wanted to see a reaction mechanism. So I hope you enjoy. Thank you. In organic synthesis, a common desired reaction involves the formation of carbon-carbon bonds between an alkyne and an aryl halide. There are many different ways to achieve alkylation, such as a Castro-Stevens reaction or a Hayama coupling. Here we talk about the coupling of an aryl halide with an alkyne via Sonogashira coupling. In 2006, Kuroda and co-workers showed a contemporary example involving the coupling of a terminal alkyne derived from D-biotin with iodinated phenylalanine, utilizing an in situ generated palladium-0 species as the catalyst. The exact electronic mechanism of this reaction is not clearly understood in regards to the copper cycle, but is believed to proceed through a classic palladium cross-coupling mechanism. Here, the palladium precatalyst species is activated to form the reaction palladium-0 compound. The exact identity of the catalytic species is dependent on the reaction conditions. In the case of simple phosphines, such as triphenylphosphine shown here, it has been demonstrated that the monoligated species is formed. The active palladium-0 catalyst undergoes oxidative addition with the aryl halides to produce a palladium-2 species. This rate-limiting step is believed to also be dependent on the utilized phosphine ligands. The palladium-2 species then reacts with copper acetylide in a transmetallation step, yielding the shown intermediate and regenerating the copper catalyst. In the next step, for facile reductive elimination to occur, the substrate groups are required to be cis to one another. If trans-stereochemistry is present, trans-cis isomerization will occur. After reductive elimination, the desired product is expelled from the complex, and the active palladium catalytic species is regenerated. As for the copper cycle, it is suggested that the presence of a base results in the formation of the pi-alkyne complex. This increases the acidity of the terminal proton, leading to formation of the copper acetylide upon deprotonation. The acetylide is then involved in the transmetallation reaction with the palladium-2 intermediate. For one of our first experiments, we attempted a copper-mediated Negishi coupling between the shown aryl iodide and alkyne and obtained a product with a moderate 60% yield. When we attempted the same reaction conditions using the aryl bromide analog with alkyne, we observed no reaction. We then turned to a variety of other Negishi coupling variations with no success. Realizing we were able to couple the electron-rich aryl bromides, we then turned to generating the aryl iodides. In one of our first experiments, we used N-butyl lithium and iodide to form the desired aryl iodide. However, 15% des-bromo product was observed by NMR. The subsequent coupling yielded our desired product in 81% yield. The issues we observed were moderate yields, messy reaction mixtures, and the inability to couple electron-rich aryl bromides. The solution to these problems was a one-pot Halex Sonogashira reaction for the potential for library expansion. Here, I took our aryl bromide starting material and performed a Williamson ether synthesis to afford a mixture of aryl ethers, with the desired ether being major. I then performed a Halex reaction, also known as an aromatic Finkelstein or Buchwald reaction, to form the desired aryl iodo product in situ using copper iodide, sodium iodide, and a diamine and dioxane at 80 degrees overnight. The following morning, I added our alkyne with some palladium tetrakis and was able to isolate the desired product in 82% yield. The diacid was then formed via hydrolysis. I then explored the scope of different aryl iodides and was able to achieve 95% yield or better. The GCMS of the crude reaction mixture showed clean aryl bromide conversion to the aryl iodide. Once aryl iodide was consumed, the crude reaction mixture showed final product with the triphenylphosphine impurity. This methodology worked for a broad scope of electron-rich aryl bromides. Crude reaction mixtures were clean, and isolated yields after purification ranged from good to excellent. So there you go, Mubashar. I hope you enjoyed the lecture, and it's a really nice method to couple electron-rich aryl bromides with alkynes. Thank you.